In this video, we'll begin our discussion of what is called the Laplace transform. This is what we'll close the class with. We'll have four sections in this unit. What we're going to do is talk about this transform. I'm going to go ahead and define it mathematically for you. And then we're going to derive some. You'll get a table of what these things are. We're going to work on a reversed transform, which we'll talk about. And then we're actually going to solve some diffie-qs with this Laplace transform. I'm going to post some other videos from Three Blue, One Brown. He does a series of three videos that are great for these. He does things in Python um, that I cannot show you. I don't have the capability of doing that. So he's fantastic. I will post that to help you understand what these are graphically and try to get a better grip outside of the mm, only mathematical approach that the book here is going to take. Okay. First things first, I want to remind you something about the linear property of integration and differentiation. What that means is that if I can like separate, notice what happens here. We took the alpha outside of the derivative, and we also took the beta outside of the derivative. We also split it across that plus sign. It like reserves the operation as another preserves the operation as another way. I talked about it in grad school, is that this linear operation keeps those things equal. I can pull constants out and I can split across plus signs and minus signs. What we cannot do is split across multiplication and division. So please, if that's you and you're still trying to do that, please don't do that anymore. Okay, so we're going to look at a transform. It's called the Laplace transform. What to start that off, the Laplace transform is an integral transform. Okay, so what this is, a transform usually takes a function and turns it into another function. So for instance, they do an example here in the middle of this paragraph where we started with 2xy squared. We took the integral and we ended up with 3y squared. It's another function. All right, so it takes a function, turns it into something else. All right, so this is an integral transform. We do quite a bit of these in mathematics, where we change the thing that is right here. What we call this is the kernel. The kernel here is going to be changed with an actual function of some sort that will define what the transform is. You'll see that in a moment as we go down, you'll see what the kernel is for a Laplace transform. Now, remember, this is an improper integral, right? So what they mean by improper integral is that upper bound is an infinity. We can't plug in infinity, right? We can think about it. We can talk about what happens as we go to it, but it would not make sense to do the integral and plug in infinity. What makes sense though is to put a variable above here, like a b or something. I think I usually put in and run a limit. So you would do your like integral first, calculate all of that, and then take the limit to figure out the infinity sign. These two things converge or diverge. When they do converge, then we do have a transform. All right, so that thing was called a kernel. What I was the k there. Um, in our Laplace transform, we are going to let our kernel be e to the negative st. Now, if you take a look at that first video in Three Blue, One Brown, talking about the Laplace transform, um, he talks about why we choose that. It's not just a random thing. These E functions are I think he called them the particles of calculus or something, like everything is created from these E's. All right, so our Laplace transform then, we use this script and I write it like this, just do a fancy L like that, and then, that parentheses and that braces, I mean. So that's how I write it. This is the notation I found in Word to use, so I'll just use that L. So the Laplace transform takes this function here, puts it in this integral to get our new Laplace transform. And we are going to start referring to the Laplace of a function lowercase f with the uppercase f. So this is what a Laplace transform is. Again, our book takes a very mathematical approach. Just like here, they're like, here's an integral transform that takes a function, turns it into another function. This is a special type of transform where we pick this function, and then now we're going to calculate a bunch of things. The book does not really go into depth, like what are we doing here? What is actually happening? And that's where those Three Blue, One Brown videos are going to come into play. For my course, you're going to have to just be able to evaluate one of these, and then we're going to solve diffie-qs with them. The thing is, though, this Laplace transform is very useful beyond this course. All right, so we're going to start. I like to start every problem off with writing the definition. So I'm going to do that here. So the Laplace of f of t is equal to 0 to infinity of e to the negative st times f of t. This is dt. Let's make sure we wrote it down. Yep, everything looks good to me. Okay, so what we're going to do now is if we're using that definition and I'm going to do the Laplace of the function 1, that gets me, and I'm going to go and change this limit. This is the limit as n goes to infinity, and we're going to have 0 to n, right, instead of the infinite bound. And then I'm going to get just e to the negative st times 1 dt. All right, this integral is not bad. It might look terrible because we have a parameter here, in this case s. So if I do a u sub here, I get negative st. Du then would be negative s dt. Remember, s is just a constant. Well, that's not there, so I'm going to do negative 1 over s du dt. All right, so we'll do that u sub. All right, we got the limit as n approaches infinity. And then we can change this. I'm going to go ahead and change my bounds too. I like doing that, meaning I'm going to plug this number right here into here to get a u. And then I don't have to worry about going back to t. I can just go to u now. So if I plug 0 in for t, I'm going to get a 0. If I plug an in for that, I'm going to get negative sn. Right? And then we replace, we're going to get an e, or sorry, let's go ahead and put our negative 1 over s, e to the negative s T. My fives and S look pretty similar. I'm gonna try to keep doing that for my S where it kind of hangs down here, while my five is a very straight edge. All right, so they do look similar. Sometimes I'm gonna do my best not to mess that up for you guys. This is now a DU. Up here though, because I was more worried about what I was about to say, that's a U. All right, we changed it to a U. That integral is now doable. I get the limit as n approaches infinity, and we're gonna get okay, so if I do this integral, I get negative 1 over s e to the u, and this is going to be ran, and these are u's. Maybe we need to write that u equals 0, u equals negative sn, right? And we're going to do that before we do the limit. All right, so we get a negative 1 over s e to the negative sn, and then we're going to get plus 1 over s e to the 0. All right, well, our limit kind of plays really nice right here. This thing, since the negative Sn is going to go to the bottom, since it's negative, this thing's going to 0. The denominator gets really big. There is no n down there, so this is just 1 over s. Okay, so my Laplace transform is, the Laplace transform of 1, just the constant, is 1 over s. Okay, there's a couple of things I want to mention here before we move on. Notice that our Laplace transform, I'm going to write it out kind of formally here. The Laplace transform of f of t, so our functions in terms of t when we start, is going to get me a capital F of s. All right, so it takes functions that are in terms of t and then puts them in terms of s. All right, so there's our first example. We'll have a video doing a few more. And that's really this whole section is. We'll just be talking about how to get from one to the other. You're going to get a table for all this, but it's good to know where it comes from. So there we go.